So this is a quick version of what I'm going to say on Friday, if you don't have other questions, because then I might say some other things. But this is essentially a presentation about central topics in my part of the course. And at the exam, you might need also to understand underlying theory and principles, and to understand concepts from previous courses, just as you need to in some of the exercises you have done. When we dealt with distillation, we used McCabe-Thiele's graphical method, and we had these mass balances we drew as lines, straight lines, and then we draw triangles between the mass balance and the system curve, the gas-liquid equilibrium. And each such triangle here is an equilibrium stage, where the flow down to the next equilibrium stage is in equilibrium with the vapor flux up to the above. So you could interpret these triangles as gas flows being the horizontal line and liquid flows being the vertical line. So in this diagram here, you see Vn is this line here and Ln is that line here. So each point on this line has a specific composition in the liquid phase. So that's the composition of Ln, and each point on this line has a specific gas composition, and that's the composition of the vapor flux. So Ln minus 1 is this line over here. That's the flux coming down to this equilibrium stage, and Vn plus 1 is the one down here, and that's the flow coming up to this equilibrium stage. Now, you can't say what the composition will be in a real tray when you do this method, because we don't draw these real trays. You could if you used the merge-free tray efficiency instead and had different efficiencies on each tray, but we don't do this in this course. So Ln and Vn are in equilibrium with each other, and Ln minus 1 and Vn are related through a mass balance, just as Ln and Vn plus 1 is related through a mass balance. And McCabe-Thiele's graphical method, we drew the diagonal, and then the upper operating line, the lower operating line, and the Q line. And well, if we're naughty, we could give you an example where you have to draw them in another order. But this is essentially the way we do it in this course. And a more difficult question would be to say, okay, you have this distillation column, it has so and so many physical trays. How far can you separate? But that's a much more difficult question. There is actually a separate podcast on the issue of what happens in a real distillation column when you change operating conditions. But that's rather advanced when compared to the rest of this course. Okay, the Q line, we had this equation, and a vertical line is saturated liquid, so liquid at its boiling point, and saturated gas, so a gas at its condensing point, is a horizontal line. And when we counted physical trays, remember that physical trays are always more than the number of equilibrium stages, because the efficiency is always less than 100%. But in order to make these overall tray efficiencies comparable between different setups, we take away the things that happen outside the column. So if you have a reboiler here, that's one equilibrium stage. And we typically have that in our course. And if you have a partial condenser, that's also an equilibrium stage outside the actual column. So in this case, when you need 7 equilibrium stages in total, if you have both a partial condenser and a reboiler, you only need 5 equilibrium stages inside the column. And when you calculate physical trays, you should always round up to an integer. So if you get the answer 13.2, then round that up to 14, because 13 is not enough. And if we ask for equilibrium stages, then we want you to answer them with 1 decimal, counting parts of a step. So here is 2.0, there is 3.0, and anything in between here is 2 point something. Here is 3 point something up to 4.0, and that's 5.0 over there. So this is exactly 3.0 here. Feed location is the triangle in the diagram that has 1 corner on each operating line. And the optimal feed location is that you change as soon as you come to the intersection of the 2 lines. So in this case, we start here on this upper operating line, and then we end, well, actually now this happens to be just on the intersection, but this still counts as 3.0, and this being the optimum feed location. So this is optimum feed location 3.0 in equilibrium stages. And if we don't have optimum feed location, then you continue to step to the upper operating line until you reach below the feed. We use dimensionless groups in this course, and we use Prandtl's number, Schmidt's number, and Lewis number, to name a few. And these 3 tells you the relation between the 3 diffusivities. So the diffusivity of momentum, the diffusivity of heat, and the diffusivity of mass. And if you have an ideal gas, those 3 diffusivities are the same, have the same value in square meter per second. When you estimate transport parameters like diffusivity, you use the first equation here for diffusivity in gases. So it's the gas constant times the temperature in Kelvin to the power of 1.5, and then you have the molar weight, the size of the molecule, a correction parameter, the pressure, and Avogadro's number. And if you have diffusivity in liquids, we have learned to use 2 kinds of equations, one for large molecules, and that one comes from a force balance. This is Boltzmann's constant there. This is the viscosity of the solution. So if you get an example where you need to use these things for liquids, note that the viscosity of the solution might be tricky, but if you have low concentrations, you can, in our course, simplify and say that the viscosity of the solution is the same as the viscosity of the solvent. But to get full points, you should better write that in your solution, that I now assume that I have the same viscosity in the solution as I have in the solvent. And if you have a small molecule, you use Wilczang's equation instead here. When we have diffusion in 1 dimension, you can use this equation here. And if it's gases, this is the molar fraction in the gas phase. And actually, if it's a liquid, this is a bit simplified, because if you add 1 liter of one substance to a liter of another substance, you don't get 2 liters. So then this equation is actually not very accurate, but still. If you have equimolar counter diffusion, you get a linear change in concentration, so linear concentration gradient. And if you have diffusion through stagnant component, well, then NB is 0 up here. Then you have a non-linear change, and it always bends in the direction of the convection. So if you get a special case that is different from these 2 cases, you have to derive your equation from this thing up here. That would be a rather difficult task for an exam, I would say. Still a possible, but a difficult task. We named some different theories and analogies. We talked about the 2-film theory, and that's for situations with more or less undisturbed films. So well-defined film with a certain film thickness. The penetration theory is when the film only survives a short time, like when you have a gas bubble that bubbles through a liquid. Boundary layer theory, we talked about airplanes, but perhaps a more reasonable example is that you have a wall that you painted, and then you have a fan that blows air along that wall, and then close to the wall you have a film that builds up. The further away you are from the fan, the thicker this film. And then we studied a mass transfer orthogonal to the painted wall. So these three theories tell you something about the relation between the mass transfer coefficient and the diffusivity, while Reynolds analogy and Chilton-Coburn's analogy, they relate different transfer coefficients, like the mass transfer coefficient and the heat transfer coefficient, as well as the transfer coefficient for momentum. And these three theories, in the two-film theory, the mass transfer coefficient is proportional to the diffusivity, straight up. For penetration theory, K is proportional to the square root of the diffusivity, and for boundary layer theory, it's proportional to the diffusivity to the power of 2/3. So why is this important? Well, it's important if you measure the mass transfer coefficient and you have an idea of what kind of theory is best suited for my experiment. And if you want to extrapolate or interpolate the mass transfer coefficient between, for example, different temperatures, you can use this relation to get a more reasonable interpolation or extrapolation of your mass transfer coefficient. And if you use Reynolds analogy or Chilton-Coburn's analogy, you relate different transfer coefficients to each other. So if you, for example, have measured the transfer coefficient for momentum, you can use these analogies to translate that to, for example, a mass transfer coefficient. In the air-water system, we use psychrometric charge and or equations for mixing. And when we do mixing, we write component balances. The water balance is G1 times X1 plus and so on. And note here that G here is in kilogram of dry air per time unit, and X is kilogram of water per kilogram of dry air, so that the mass balance becomes kilogram of water per time unit. There should be no cubic meters in here in this equation, because then it gets totally weird, because the volume changes if the temperature changes, and the volume changes also if the amount of water changes. So please do not use cubic meters here, because that will produce totally bogus results. And for air, the component balance is simply G1 plus G2 equals something. Energy balance is similar to the water balance. You just take G1 times H1 plus and so on. So G1 is again kilogram of dry air per time unit, and the enthalpy is in kilojoule per kilogram of dry air. The wet bulb temperature is an energy balance between evaporation from water surface and heating by surrounding air. And the equation there is difficult to use. So if you get an example with a wet bulb temperature, then just use the psychrometric chart, because it's been calculated for you, and you don't have good enough data to see how the heat capacity changes with temperature and how the evaporation enthalpy changes with temperature.